Okay. So, yeah. So let me get my. All right. In this supplement, I want to talk with you about. Well, I'm not talking with you. I'm really talking at you. So, which I actually hate more. I'd rather have the feedback. But at any rate, I want to talk about counting number systems and place value. And I understand that this may seem really elementary or even kindergartenish. I mean, counting. I mean, come on, everyone can count. Why are we covering this? And okay, that's true. People have been counting in base 10 all of their lives and really don't have much of an issue with it. And we might even go further and say that enough people understand the units column and the tens column and the hundreds column and the thousands column to make this seemingly somewhat under par, but or trivial for this level. Um, but I think that really what isn't as common. People don't take the time to abstract the way we count, the algorithm that we use to count, and apply it to other numbers, such that it can be applied to other number systems. And this is really, really, really useful, as it turns out, because if you can count in another number system, then you can do math in another number system. I mean, if you think about it, counting is really just, or adding is just really counting. I'm going to count to five, and I'm going to count three and more, and oh my God, I have eight, right? It's really, and multiplication is just repetitive counting. So I'm going to count to five, seven times, and oh my God, 35, wow. And on the reverse side of it, subtraction is just counting backwards. And division is just repetitive subtraction. So if you can count in another number system, and you are well on your way to being able to do math in that system. And moreover, as we'll see in a bit, the expanded this when we look at the algorithm of counting, this process of counting, we expose this idea of the expanded form and place value, which allows us, I should say, we expose the idea of place value and with it expanded form, which allows us to convert any number system back into decimal. And that's just awesome. So I think you'll find that this is really, really useful. Okay, so let's go ahead and get into it then. Number systems are made up of enumerations of digits. So an enumeration is a complete and ordered set of objects. So if we look at base 10, our enumeration of digits is 0 through 9. We don't have any more than 9, so the set is complete. It's an ordered set. We count 1, 2, 3, 4, 5, 6, 7, 8, 9 in that sequence. We don't count 2, 5, 3, 1, 6, 7, 8, I mean, unless you're like some kind of mad statistician or something. Actually, I really shouldn't pick on the statisticians. And statistics is a great, very useful thing that we'll get into here a little bit later in the quarter. But we count in sequence, so the set is ordered. So it is an enumeration. It is a complete and ordered set of digits. Again, base 10, our enumeration is 0 to 9. Oh, I should, let me, where is, I should say that number sets are further defined by their radix or their base, and these terms are interchangeable. So the radix or base are the number of unique digits that make up a numbering system. So the radix for base 10, well, the enumeration is 0 through 9 for 10 unique digits. So we have a base 10, so that's our radix. In octal, our enumeration is 0 through 7. These are our digits. There are 8 unique digits, so for base 8. In quintal, or base 5, we have 0 through 4 are our digits. That's our enumeration. For a total of 5 unique digits, so we have base 5. In binary, we only have the 2 digits, 0 and 1, for base 2. And now hex is really interesting, at least I think so, because hex, the radix is 16, but our normal counting system only goes to 9, right? We only have up to the number 9. So how are we going to deal with these extra digits? And what we decided, and well, I mean, we didn't decide. I didn't decide. They didn't call me up and say, James, man, what should we do? I'm like, I think, and probably it's best that they don't ask my opinion, to be honest. But so what was decided, let's say, is that the letters A, B, C, D, E, and F would be added in on the back side of the 9 to fill in the gap there, or the rest of it to fill it out. So our enumeration is 0 through F. A taking a decimal value of 10, B taking the decimal value of 11, 12, 13, 14, and 15. Next one over for 16. So when we count in hexadecimal, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F, or I suppose we might go, A-teen, B-teen, C-teen, D-teen, E-teen, or F-teen, maybe? Or maybe not. Yeah, maybe not. See, this is why they don't call me for my opinion, but okay. So that's how we count in hex. If we're counting in say, quintal, we would count 1, 2, 3, 4, 10, 11, 12, 13, 14, 21, 22, 23, 24, etc. So we just start over much earlier. So if we look at this, as far as we abstract out this process that we're going through, it works like this. We simply run up the sequence of our enumeration. So we're just running up this way until we run out of digits. So once that point where we run out of digits, when the next count falls, we have no place to put it. So we bundle everything up as a set of the radix and move it over here. Okay, and it is a set of the radix because when we reach here, that next one falls. So if like this were 1, 2, 3, 4, on the fifth one, we bundle up that set of 5 and move it over. Okay, so we move over a set of the radix here and we increase this column by 1, reset this back to 0, and start again up the enumeration till we can't go any further. When the next count falls, that becomes a set of the radix that gets moved over here. Okay, cool. This process goes on ad infinitum, actually, but we'll stop. We won't go that far. Only Chuck Norris can count to infinity. Twice, I'm told. Anyway, sorry. So once we fill up both columns, when the next count falls, we bundle up this just as we've been doing. We bundle up the set of units and we move them over here as sets of units. But we don't have any place to go here because we're out of digits. So we bundle up our set of units into sets of units and move them over here. And we increase this by 1. So we're working with sets here, and that's kind of what I want to point out, and I want to keep in mind that really what we're dealing with here are sets. Okay, at least here. So once we're here, we then, of course, start our process again on until we reach, I'm just going to fill it in. I'm not going to count all the way up, until we get to here. And now when the next count drops, we bundle up here into a set of units, move it here. We have no place to go. So we bundle up our sets of units into sets of units and move them over here. And again, we have no place to go. So we bundle up our sets of units into, yep, you guessed it, sets of units, and we move them over here. So that's really what I want to drive at, is this idea that here we're working with, give us some room here. Here we're working with units, So we're not working with any sets at all. Here we're working with sets of units, so we're working with single sets. Here we're working with sets of units, so we're working with what we might call double sets. Here we're working with sets of units, so we're working with 3. And this becomes our place value. So that's what we're driving at now, is this idea of place value. Wow, writing in this. You know, this pen, I apologize. My tablet is so awful. I mean, you want to talk about things that are kindergartenish. My writing is just atrocious here with this tablet. It's horrific. At any rate, so we're working with place value, and place value works like this. You simply take the base and its positional value, which is the number of sets that you're working with. So base raised to the power of the number of sets we're working with. If we're working with 10, say, we have 10 to the 0, which is 10, or units, or 1. 10 to the 0 is 1, so everything we're working with here is units. In this column, we're working with sets, 1 single sets. So we have base to the power of 1, or if we're, again, back to working in decimal, because we're used to that, we have 10 raised to the power of 1. So 10 raised to the power of 1 is 10. So this is our tens column. Here, of course, we take our positional value, our place value is base times, or base raised to the power of 2 sets, because we're working with sets of sets, or tens of tens, which are hundreds. It's not horrifying looking. Tens of tens, which are hundreds, or 10 to the second. And then here, of course, our base, because we're working with sets of units, we're up to 3. So our base raised to the power of 3 is our positional value or place value, or 10 to the third, which is the thousands column. Okay. Now, if we were to do this with binary, actually, let's not go there yet. Let's look here at, so then what we have is if we place any number here, we can further into the extended, I don't want to make that look like a division, working its way into, this is the, stop that, okay. Working our way into the extended form. And extended form works like this. We take whatever number we may have in the column, multiply it by the positional value. And each column is added together. Okay. So the column I'm in here is whatever number y times b squared plus y times b to the first plus y times our base to the 0. And here it's y times b to the third. So this then becomes our extended form right here. As you can guess, I'm not any good at the computer drawing games. It's really bad. Okay, so this is our extended form, abstracted into y's and b's and powers. In base 10, it would, of course, let's say, let's put some numbers in here and look at what it might look like in base 10. So if we had 1,327, right? We take this y times our base to the 0. So this is 7 times 10 to the 0, which is 1. So 7 times 1. That's why we get our units. Plus 2 times 10 to the first, or 10. So 2 times 10 is 20. Plus 3 times 10 to the second or 100 for 300 plus 1 times 10 to the third or 1,000. So again, 10 to the 0 is 1, so 7 times 1 is 7. 10 to the first is 10, so 2 times 10 is 20. 3 times 10 to the second, 10 to the second is 100, so 3 times 100 is 300. And then finally, 1 times 10 to the third is 1,000, so 1 times 1,000 is 1,000. So the value of our number here is 1,000 plus 300 plus 20 plus 7, or 1,327. Okay. Again, yeah. Okay, so let's go ahead and look at that then in binary for a moment. Let me get rid of this. Okay. And get rid of all this up here. If we're going to do this count in binary, the way we count in binary, of course, we start with 1 or 0. So we add 1, and in our next count, when our next count falls, we have no place to go. So we bundle that up as a set of 2 and move it over here. And now we have one set of 2, and we go ahead and reset this back here. And then when this falls, and then we count 1, and when the next count falls, we have no place to go, so we bundle up this and we set of 2 and move it over here, and then we have no place to go here, so we bundle up this set with the set coming in for a set of sets, and we move it over here like that. Okay, all right. And then we reset everything back over here to 0. And we go ahead and then we count 1 here. On our next count, we have no place to do with it, so we move it over here. No place to go with it. We have 1 here. We reset this. And next count, again, we count upward again like this. And then on our next count, we have enough place to put it. So we bundle that set up and move it over here. We have no place to put this one. So we bundle up the sets of sets and move them over here. We have no place to put this. So we bundle up the sets of sets into sets of sets of sets and move those. Whoops, that should have been like that. Move these into sets of sets of sets over here. And we put that one there and then reset everything to the right. So this is counting in binary. And when we look at this, if we have digits in here, or when we have digits here, we can actually apply our expanded form here in order to convert this back to its decimal value. So let's say, for example, that we have put some digits here. And so here we have 1 times b to the 0, which is, in our base, is 2. So 2 to the 0, which is 1. So 1 times 1 is, of course, 1. Here we have 0, 2 to the first, or 2. That's plus. 0 times 2 to the first. 2 to the first is 2, but 0 times 2 is 0. Here we have 2 to the second, which is 4. 1 times 2 to the second. 1 times 4 is 4. I'm missing my pluses here. Here we have 2 to the third, which is 8. And we have 1 here. So we have 1 times 8, which is 8. So when we fill this in, we have 1 here, 0 here, because 0 times anything is 0. this is 1, 2 to the first, 2 to the 0 is 1, 1 times 1 is 1, 0 times 2, 2 to the first is 2, 0 times 2 is 0, 2 to the second is 4, 1 times 2 to the second, or 1 times 4 is, of course, 4, and then 2 to the third is 8, 1 times 8 is 8, so the decimal equivalent here is 13. 8 plus 4 plus 1 for 13. So we've now converted that number back in. Okay, so we can see that expanded form allows us to convert this back into its decimal form, its decimal equivalent. Okay, 1 second here. So let's see, we get rid of this. Now I want to look, I want to look at addition and subtraction and how counting applies to addition and subtraction. But just before I do that, I want to revisit just a couple of things that are really important, because this converting is, we're going to go over it again in the future and in the next couple of sections. And arithmetic, we're going to go over in the next couple of sections. So we're going to revisit this stuff. So what's important here is the idea of expanded form and place value. And b to the second, and b to the first, and b to the 0. These are place value. Okay, so our place or positional value and our expanded form is here. So I want to make sure that we understand place value and expanded form. And place value is very interesting because it it makes working in binary really very easy. Because if you look at it, again, what we had up here before, if you look at it, anything here, 2 to the 0 is 1. So if I have a number here, it's 1 times 1, which is 1. If I have, here's 2 to the 0, or 2 to the first, sorry, which is 2. So if I have 1 times 2 to the first, I have 2 here. If I have, here we have 2 to the second, which is 4. If I have a number in this column, I have 1 times 2 to the second, which is 4. Here I have 2 to the third, which is 8. So if I have a number here, I have 1 times 2 to the third, which is 8. Okay, all these added together. So really what the 1 does is it kind of turns on, binaries on and off. So the 1 kind of turns on that column and allows us to add it. Other than that, it's just straight positional value. So like what I mean is, if this is 0, if I don't have anything here, if this one is 0, pardon me, 2 to the first is 2, but oops, that is supposed to be a dot. 2 to the first is 2, but 0 times 2 is 0. So this column, in effect, just shuts off. So we don't really need to worry about the expanded form so much in binary. We can simply try to remember the values of the columns. This is very easy to do when we're only working with, like, say, 4 columns. Let me get a slightly bigger eraser here. Again, if we 2 to the first, if we have a number here, then we get the value of 1. because 2 to the 0 is 1, and if we turn it on, 1 times 1 is 1, 0 times 1 is 0. So if it's on, then we have a 1 in this column. Here we have 2 to the second, which is 2. If we have a digit here, 1 times 2 is 2, so it just turns it on. If we don't have a digit here, 0 times 2 is 0. Here, 2 to the second is 4. So if we have a 1 in this column, then it's 1 times 4, which is 4. If we don't, then it's 0 times 4, which is 0. So we just turn on that 4. Here we're going to turn on or off an 8, and it just keeps going up. 16, 32, 64, etc. Okay, so gotta get rid of some of these here. What I'm saying is you don't have to actually do this multiplication. You don't have to multiply. You can sort of short circuit the extended form by simply noting where we have digits. So I have 2 plus 8 for 10. As simple as that. If I change it up, I have 2 plus 4 plus 8, or 12. So it's fairly easy to do convert binary back into decimal. You don't have to actually go through this whole method if you memorize the place values, and they're easy to memorize because they just double each time. 1, 2, 4, 8, 16, 32, 64, 128, blah. Okay. So before we wrap this up here, I want to look at just how all this affects, how counting affects arithmetic, because I said that if you can count in a system, you can do math in that system. So let's look at this. We'll start off with some decimal because we're all very used to that. So 298, and we'll add to that, say, 18. And what I want you to note is that when we do 8 plus 8, we have 16, and we can't represent that in our system. It goes up to 9 in base 10. So we drop the units of 6 off, and we bundle up that unit of 10, that set of 10, and move it over to the next column here. So we're really not carrying a 1. We're actually carrying a unit, a set of 10. And I think that that's sort of a misnomer that tends to confuse people when it comes to certain moments in mathematics, that we're really moving a set over here. So here we have 9 sets of 10 plus one set of 10 plus another set of 10 for 110. Sorry, 11. So we drop off the 10 here, and we move the set of sets of 10 over here, and this becomes then 300. I misspoke back there. I apologize. But this is 9 sets of 10 plus 1 set of 10 plus 1 set of 10. Okay. So when we subtract, we're basically doing the same thing. We just have to bear in mind what sets we're working with. So if we're doing, like, say, 212 minus 78, okay, I can't pull 8 out of 2. I end up in the negatives. But what I can do is borrow a set of 10 from here. I'm not borrowing 1. We always say, oh, borrow 1, but we're not. We're borrowing a set of 10. So when I move this, that should be a 0. I'm trying to get that to right, 0. Okay, so I borrow this 10 over here, and really what I'm doing is I'm taking that set of 10, turning it back into units. So now I have 10 units plus 2 for 12. So when we borrow the 1, we kind of just put it down there and make it a 12, but we're really borrowing 10 and adding that to the 2 to make it 12, and then moving this down here for 4. So we're taking 8 out of 12 and giving us 4. I can't take 7 from 0, or more to the point, I can't take 70 from 0. But what I can do is I can borrow a set of sets. So I cross this out and make that 1. And then I'm going to borrow a set of sets over here and turn that into 10 sets of 10, or 100. So I'm really pulling 70. I don't have room to write it. I'm really pulling 70 out of 100, but we just drop the zeros for convenience, and it looks like 7 out of 10. So that's 3, and then 134. So bearing in mind that we're really working with sets in this sort of short-circuited way of looking at it is really important, because when we get into binary, it tends to get a bit more confusing. And what the book has you do is memorize these tables, and I don't think that that's really necessary. If we look, say, at this problem here, right, and we're going to look at what carrying, back to this idea of carrying over. 1 plus 1 is 2. Now I can't write a 2 down in my system, so but I can bundle it up and move a set of 2 over. So I have nothing left over, because when I move a set of 2, I have nothing left here. So I move that set of 2 over here as a single set of 2. So I have one set of 2, another set of 2, another set of 2. So 1, 2, and 3. Now I definitely can't write that down. If I can't do 2, I can't do 3. But I can pull a set of 2 and move it over here. So what that leaves us, though, then is we're actually going to drop off one set here and then move a set of 2, a set of sets of 2, sorry, over here. And then that gives us 1 here and then 1 there. Okay. So basically, the point I'm trying to make is that we're moving, when we went this way, we bundled up a set of 2 and moved it over here. And here we had a set of 2 and a set of 2 and a set of 2, which gave us 3 sets of 2. I can bundle up 2 of those sets of 2 and move them. I can bundle up 2 of those sets of 2 and move them, leaving 1 set behind and moving that 1 set over here. So that's kind of what I wanted to bring forward, is what we're bundling up and moving sets. Okay. When we're subtracting, we get basically the same thing. So we take and then let's see, we'll subtract it from this. No, I can't subtract 1 from 0. So I have to borrow from here, but I'm not borrowing 1. The book has you borrowing 1, and that really, I think, is somewhat confusing. What I'm really borrowing is 2. Okay, so 2 minus 1 is 1, and then that becomes 0 and 0 and 0 and 0. Okay, so I actually did, you see that these are 1 digit apart. Wait, hold on a second, I need to drink something, hold on. And the reason I say that this is important to note, we'll kind of do this sort of the wrong way, and I'm going to put it in red so we know that so it's wrong. If I'm not careful and think about what I'm doing, I either have to memorize the table, or I can just pay attention to kind of what I'm doing. And I think it's useful to understand this because, otherwise you end up trying to borrow 1, and that's not going to work. So if I say, okay, I can't take 0 from 1 or 1 from 0, so I have to borrow 1, right? And you don't. You're not borrowing 1, you're borrowing 2. You're borrowing 1 set of 2. Because if I take this and I move it over here as a 1, then I get 1 minus 0, 1, which is 0, and I am wrong. Okay, this problem is now gone. It's invalid. It's not going to work. So this borrowing 1 concept, I think, can be really dangerous in binary. Remember, you're borrowing a set of 1, so you're borrowing 2. Cool. All right. And that's kind of where I wanted to get to. We'll get into this again next time. So thank you for your time, and we'll talk to you later. Bye.